Hello, I'm Professor Von Schmohawk, and welcome to YU. In the previous lectures, we introduced exponential and logarithmic functions as closely related transcendental functions and said that logarithmic functions are the inverse of exponential functions. We saw how the work of Swiss mathematician Jacob Bernoulli in 1683 led to the development of exponential functions. However, logarithms were introduced many years before exponential functions were conceived. In 1614, Scottish mathematician and physicist John Napier introduced logarithms as a means of simplifying tedious calculations involving multiplication or division.
Seeing there is nothing that is so troublesome to mathematical practice, nor that doth more modest than hinder calculators, than the multiplications, divisions, square and cubical extractions of great numbers, which besides the tedious expense of time, are for the most part subject to many errors. I began therefore to consider in my mind by what certain and ready art I might remove those hindrances.
So let's see how logarithms can be used to simplify the process of multiplication and division. As an example, let's say that we wish to find the product of 827 times 396. Before logarithms were introduced by Bernoulli, the results of multiplication had to be obtained by the tedious method of long multiplication. For example, to multiply 827 times 396, we start by multiplying the top number by the ones digit of the bottom number. So to multiply 6 times 827, we first multiply 6 times the rightmost digit, 7. 6 times 7 is 42. So we bring the ones digit of 42 down below the rightmost column of numbers, and we write the tens digit above the next column to the left, becoming the carry digit for that column. We then multiply 6 times the next digit to the left, 2. So 6 times 2 plus the carry digit 4 is equal to 16. We then bring the ones digit of 16 down below the middle column and write the tens digit above the next column to the left, becoming the carry digit for that column. Finally, we multiply 6 times the last digit to the left, 8. 6 times 8 plus the carry digit 1 is 49. So we bring the ones digit of 49 down below the left column of numbers and write the tens digit above the next position to the left, becoming the carry digit for that column. And since any numerals in that column would be zeros, the sum for that column is 4. Now the next step in this multiplication process is to multiply the top row by the next digit to the left, 9. Going through the same steps as before, we get 7,443 shifted one column to the left. And finally, we multiply the top row by the last digit to the left, 3, giving us 2,481. We must now add these three partial products, giving us the answer 327,492. From the example we just saw, it is easy to see why the revolutionary invention of logarithms by John Napier quickly became popular. Using Napier's logarithm tables, multiplication and division involve only the much simpler process of addition or subtraction. This is the result of a unique property of logarithms. For any two positive numbers, a and b, the logarithm of a times b is equal to the logarithm of a plus the logarithm of b. Likewise, the logarithm of a divided by b is equal to the logarithm of a minus the logarithm of b. So let's see how this property of logarithms can be used to simplify the tedious process of long multiplication and division. The key to using logarithms to multiply and divide was a set of tables created by Napier that allowed numbers to easily be converted to logarithms and logarithms to be converted back to numbers. If we want to multiply two positive numbers, using Napier's logarithm tables, we convert these two numbers to their logarithms and then add those two logarithms. Since the sum of the logarithms is equal to the logarithm of the product of a times b, using the logarithm tables, we convert that logarithm back to the product of a times b. Likewise, if we want to divide two positive numbers, we look up the logarithm of each number and subtract those two logarithms. Since the difference of those logarithms is equal to the logarithm of a divided by b, using the logarithm tables, we convert that logarithm back to the quotient of a divided by b. Napier's logarithm tables were rapidly adopted by navigators, scientists, engineers, and many other professions to perform computations more easily. Later, the logarithmic slide rule was developed, allowing multiplication and division computations without the use of tables. But more recently, in the 1970s, electronic calculators were introduced that could perform logarithmic calculations with more precision, replacing the need for slide rules. So let's see how logarithms work and why logarithmic functions are said to be the inverse of exponential functions. When we introduced exponential and logarithmic functions, we said that logarithmic functions are the inverse of exponential functions. Exponential and logarithmic functions both involve the same three quantities. The first two quantities in an exponential function are the constant base value raised to the power of a variable exponent. The third quantity to consider is the value that results from the base raised to the power of that exponent. The difference between an exponential function and a logarithmic function is which two quantities are given and which quantity must be determined. In an exponential function, the base and exponent are given quantities, and the resulting value must be calculated. On the other hand, in a logarithmic function, the base and resulting value are given quantities, and the exponent that produced that value must be determined. The process of determining the value of an exponential function is straightforward. Its value is determined by raising the base to the power of its exponent. For example, if the base is 3 and its exponent is 2, we simply calculate 3 squared, which is 9. On the other hand, with the logarithmic function, if the base is 3, and the value of 3 with the unknown exponent is 9, the value of 3's exponent must be determined. We could determine the value of that exponent by trying different exponents until we find one that produces a result of 9. In this example, the exponent's value would be 2, since 3 squared is 9. A logarithmic function is simply a way of expressing this process, and it is written as follows. First, to indicate that the base is 3, we write log with a subscript of 3. Then, to indicate that the value of 3 with the unknown exponent is 9, we write 9 after log subscript 3. So the value that must be determined for this function is the exponent that 3 must have to produce a result of 9. Since 3 squared is 9, the exponent of 3 must be 2. We say the value of log base 3 of 9 is 2. So to evaluate a logarithmic function of x with a base b, we ask what must the base's exponent be for the result to be x. To see some examples of this process, let's evaluate a few basic logs. We will start by evaluating log base 3 of 9. So we ask, what must 3's exponent be for the result to be 9? Since 3 with an exponent of 2 is 9, the value of log base 3 of 9 is 2. As another example, let's evaluate log base 10 of 1000. So we ask, what must 10's exponent be for the result to be 1000? Since 10 with an exponent of 3 is 1000, the log base 10 of 1000 is 3. As another example, what would be the value of log base 10 of 1? So what must the exponent of 10 be for the result to be 1? Since any non-zero number with an exponent of 0 is 1, the log base 10 of 1 is 0. As one last example, let's evaluate log base 10 of 1/10. So what must this base's exponent be for the result to be 1/10? Since any number with a negative exponent is equal to 1 over that number with the same positive exponent, 10 with an exponent of -1 is equal to 1 over 10 with an exponent of +1, or 1/10. Therefore, the log base 10 of 1/10 is -1. So now that we have evaluated a few examples of logs, let's try graphing the logarithmic function of x, log base 2 of x. We will start by evaluating log base 2 of x for an x value of 8. Since the log's base is 2, we ask what power of 2 is equal to 8. Since 2 cubed is 8, the value of log base 2 of 8 is 3. Graphing this result, when x is 8, the function has a value of 3. So now let's evaluate log base 2 of x when x is 4. We now ask what power of 2 is equal to 4. The answer is 2, since 2 squared is 4. So the value of log base 2 of 4 is 2. Adding this point to our graph, when x is 4, the function's value is 2. Next, let's evaluate the function when x is 2. Now we ask, what must the base's exponent be for the result to be 2? Since raising a number to the power of 1 doesn't change that number's value, the base's exponent must be 1. And so the value of log base 2 of 2 is 1. So when x is 2, the function's value is 1. Next, we will evaluate the function for an x value of 1. So what must the base's exponent be for the result to be 1? Since any non-zero number with a 0 exponent is 1, the exponent of 2 must be 0. So the value of log base 2 of 1 is 0. Graphing this result, when x is 1, this function's value is 0. Now, let's evaluate this function when x is 1/2. So what must the base's exponent be for the result to be 1/2? The answer is -1, since 2 with an exponent of -1 is the same as 1/2 with an exponent of +1, which is 1/2. Therefore, the value of log base 2 of 1/2 is -1. So when x is 1/2, this function's value is -1. Likewise, when x is 1/4, what must the base's exponent be for the result to be 1/4? In this case, the exponent must be -2, since 2 with an exponent of -2 is the same as 1/2 with an exponent of +2, or 1/4. So the value of log base 2 of 1/4 is -2. So when x is 1/4, this function's value is -2. Earlier in this lecture, we said that logarithmic functions are the inverse of exponential functions. This is true whenever both functions have the same base value. For example, the function log base 2 of x is the inverse of the exponential function with the same base value 2. The graphs of these two functions are similar in several ways. For example, the two graphs are mirror images of each other, mirrored around a 45-degree line running through the origin. The exponential function's asymptote is the x-axis, and its graph crosses the vertical axis at a value of 1. Likewise, the logarithmic function's asymptote is the vertical axis, and its graph crosses the x-axis at an x value of 1. So why are these two functions called inverse functions? One way of thinking about inverse functions is that one function undoes the other function in the same way that a square root function undoes a square function for non-negative numbers. If we square 3, the result is 9. And if we take the square root of 9, we get 3. Likewise, exponential and logarithmic functions act as inverses to each other when both functions have the same base. For example, if the exponential function's base of 3 has an exponent of 2, the function produces a value of 9. And if we take the log base 3 of 9, we get 2. So far, we have seen how logarithms were initially created to simplify long multiplication and division into the much simpler processes of addition and subtraction. We also saw how logarithmic and exponential functions are the inverses of each other, involving the same three quantities. In the next lecture, we will explore more features of logarithms and see how logarithms are used today.